I can't hear anything, sir.
I think he's still sorting out the visualizer.
Sorry, I had some technical problems. I hope now you can hear me and you can see the visualizer. Is it
Yeah,
okay?
yeah, we can see.
Okay, I'm sorry, there was a technical issue with the visualizer, so I had to move to a different building. Okay, now, last time we started with the method that we called the Gauss elimination method for um, solving linear systems of higher order, third degree, and so on. Now, this Gauss elimination method, so I hope you can see it now. Solving. So our topic still solving systems of linear equations. So the first method, I'm talking now about the higher order, of course. Lower order, we had techniques like substitution and so on. So this is the Gauss or Gauss-Jordan elimination methods. And these are entirely using the so-called elementary row operations that we did actually this morning in the tutorial second assignment. So the method there, Gauss elimination, you just reduce to an upper triangular method, matrix that we call the echelon form. And the Gauss-Jordan goes all the way to the so-called reduced echelon form where you have the identity and you solve the linear system. Now, another method that we will be learning today and next week, two methods actually, using the matrix index inverse, where A is the coefficients matrix. So you write the system in the so-called matrix form. And our goal for today is to develop a method to evaluate this particular matrix inverse. And of course, using an inverse, here it doesn't exist always. So if it exists, so A inverse is not defined. So if it is, it exists, let's say. Okay? So it's not granted that A inverse exists for every matrix. So it will see that it exists for matrices that have as many rows and columns that we call squared matrices. And of course, the determinant should not be zero. So we'll learn some techniques how to evaluate this A inverse. Now, why this is important? Because if I know A inverse and assume it exists, then I will multiply here from the left with A inverse. So I will multiply it here, of course, and there. So then I will get A inverse matrix multiplication by A with X is equal A inverse B. But A inverse times A is the identity matrix, and the identity matrix multiplied by the variables matrix X, and this is a solution for the linear system. So this method, if you know the inverse of the coefficients matrix, you multiply it from the left with the right-hand side, and you are done. This is the solution. Another method that we will learn next week is the so-called Kramer's rule. Sorry, Kramer's rule. And Kramer's rule entirely depends on the determinants. This we will discuss next week. So make sure that if you have still problems with determinants, evaluating them in particular 3 by 3, sometimes 4 by 4 determinants, just to refresh your memories. Now, as you see here, this method that is our topic for today, it requires two things that we need to learn today. Here, if you look at this equation, capital X here is the variables matrix, of course, and this is, of course, a solution we are looking for. Now, here, two things. We need to define the multiplication of matrix. So this is matrix multiplication, and also to develop a method to evaluate the inverse of a given matrix. Okay. Now, before I start, I just want to remind you about what we did last week. So last week we defined matrices. We defined special types of matrices. And we started by defining basic operations on matrices, in particular, addition and subtraction. So I assume that you all went to school, sometime elementary school, and you learned the operations on real numbers or numbers in general. So you learned addition, you remember, and subtraction. And when we talk about operations on matrices, as I mentioned, this is not defined always, okay? It's not always defined. So I have here. Not like numbers, okay? When I tell you 3 plus 5 or 3 times 5 or whatever, you will not think whether it's defined or not. So it's granted that there is a result for this. However, when we talk about matrices, the operations are not defined. For instance, here, addition and subtraction, like we saw last time, they must be having same dimension, okay? So I am adding an n times m matrix to a same dimension matrix, meaning it has as many rows and columns, and we saw that we do it, each position or each index is added to the corresponding index. Now, when it comes to multiplication, and division, right? I assume these are the 4 operations you learned at school, basic operations. Now, for matrices, we will define multiplication today, and multiplication of matrices here, it depends on the concept that we use for vectors, which is the dot product of vectors. Now, if we require that, or recall that this dot product of vectors, it's only defined if the vectors have same dimension. That's why we will see that there's a constraint here that not always multiplication of matrices is defined. So it's only defined if we are capable of using this dot product fact that it must be the same dimension. I will tell you more in that as we proceed today. But division of matrices, it is not defined. It doesn't make any sense. So it's not defined. There is no division of matrices. So when we talk about matrices, we can talk about addition, subtraction, multiplication of matrices, but there is no division. However, still we can solve problems involving equations of matrices. If you remember, now I want you to help me out of that. If I tell you 3x minus 6 is equal to 9, okay? How will you solve? Now forget about matrices in numbers, okay? X in R, not a matrix. Okay. How you proceed here?
You collect the like terms, like 3x, you take 6 to the other side,
3x is equal to
9 plus 6.
9 plus 6. Okay. Then, of course, here solve means solve, find x equals value for x. When you solve, so you have in mind that you ultimately want to get x, right? Then next step, what do you do? So here 15.
Yeah.
15 divide 3 equal 5.
You divide by 3, yeah? Divide by 3, okay? So here 15 divided by 3, and it's equal to 5. Now, if we are talking about matrices, we don't have division of matrices. So this step here, we can add and subtract, but this step here, we don't have division. So what to do here? Notice that here we divided by 3, but division by 3 is just simply multiplying by the reciprocal of 3, which is the inverse of 3 under multiplication. Okay, so this is the trick we are going to use to solve the equations with involving, of course, matrices. Since we don't have division, no problem. We multiply by the inverse to get the identity. Okay, so this is how we proceed. Okay, let's define the matrix multiplication. So I thought that this is a little bit too abstract, so that's why I just want to discuss with you some real life problems when we talk about it. So real life problems, and let me see here. I have this file. Okay, so let's start by defining the multiplication of matrices. And I'm going to do it in hand of an example rather than abstract. So let's assume I have two matrices. Okay, so let's say I have two matrices, A and B. So this matrix has 1, 2, 3, 4, 5, 6. And another matrix that has 7, 8, 9, 10, 11, 12. Okay, before we start, here the multiplication, I will just use sometimes cross, sometimes we will use dot, and later we will just work as numbers. If you have AX, it means it's A and X are matrices, then it means multiplication, okay? Now, as you see here, before we start, what are the dimensions of these matrices? So who's going to tell me what's the dimension of this matrix to the left? You remember we agreed that we write rows, right? Times columns. So this is what we agreed on, okay? This is the dimension of a matrix. Number of rows multiplied by number of columns. This matrix, what is the dimension of this matrix? How many rows I have here?
It's 2 by 2.
2 into 3.
2 by 3, right? Okay. This one, 1, 2, 3. So it's 3 by 2. 3 rows, 2 columns. Okay. Now here the rule, it says that the first matrix has as many columns as the rows of the second matrix. Okay. So this is defined if number of rows of first matrix is equal number of columns, sorry, so number of columns here of rows of the second matrix. Okay. Now, why is this the case? What we are going to do, we are going to take this row and multiply it with this column. If this is the case, the number of columns there and the number of rows here are equal, that means here I can perform the dot product because they will be definitely have the same number of elements or same dimension. So here I have three, let's say, dimensional vector. I can perform the dot product with another three-dimensional vector. So if this let's say equality does not exist, then we cannot talk about the multiplication of matrices. So in order to perform, or before you start multiplying matrices, you need to think about the or you need to check whether it's defined, the operation is defined. Otherwise, it doesn't make sense. Okay, now I want you to pay attention. It's a little bit. So if this is A, this is B. Let's say that the product is the outcome here of this product is the matrix C, and let's assume this matrix C. Of course, it has. Now, what is the dimension of the output matrix? Now, the output matrix here, it has as many rows as the first one, as many columns as the other one. So if you like here, if you put the dimensions, you compare these inner values. If they are equal, that the multiplication is defined. If it's defined, then this one times this one is the number of the rows and columns in the outcome. So this one here, it will be 2 by 2 matrix. And here you will be having C11 first position, C12, C21, and C22 are the indices of this matrix. Okay? So here, this 2 comes from here. This 2 here, number of columns come of that one. I hope it's clear. Now, what is the outcome of here? Now, let me just do it a little bit, maybe more. Now, if you multiply this row with this column as dot product, okay? So this is here dot product of vectors. Here, this will give me this particular location C1, okay? So anyone can tell me what's the outcome of this one if you multiply it out? You remember the rule for dot product, or do you want me to repeat this? Rule of dot product of vectors: multiply first element with first element, add it to multiplying second with second, third with third. Okay? So here, if you like, it's 1 times 7 plus 2 times 9 plus 3 times 11. Okay? So what is the outcome here is 58, right?
Right, 58.
Is it clear how we found out this first element?
Yeah.
Okay. Now the second element here is just the outcome out. So we generate here the entire first row by multiplying this row first with this column, then this with second column. So the second element here, it will be the outcome of multiplying these two, 1 times 8, 2 times 10, so 28, and then 3 times 12, 36. So all in all, what do we get here? 64, right? Okay, is it clear where we got this 64?
Yeah.
Okay, now we go to the second row. Let me use another color. So this row here, I multiply it here with the first column. 4 times 7, 5 times 9, 6 times 12. Sorry, no. 4 times 7, 5 times 9, 6 times 11. So I get here 66 plus 45 plus 28, 139,
And 39.
right? 139. So here I got 139. The same here, I multiply this second row with the second column, 4 times 7, 4 times 8, 5 times 10, and 6 times 12. And I got here 54, 154. Okay, so I will give you an example in short why how this is, how this fits actually in real life. Okay, how this fits in real life, because obviously there are lots of real life applications that can be solved using the matrices and matrix arithmetics. Any questions regarding this? Multiplication of matrices is, as expected, is defined differently. First of all, check whether this operation is defined at all before you trying to evaluate it, because otherwise it makes no sense at all if you try just to evaluate something that is not defined. Okay, it's just like if you are in a building that has 3-story and I ask you to go to the 5th floor, then you will just think this is not possible because it has only 3 floors. And here, if it's not defined, you can't do anything about it. Questions?
Yeah, I have a question.
Yes, please go ahead.
Is it we've multiplied the 2 by 3 matrix by the 3 by 2? Will you get the same result if you multiply the 3 by 2 and the 2 by 3?
You are asking about the outcome?
Yeah, will the outcome
Yeah,
be the
yeah.
same?
Okay. In general, if you have an n times m matrix and you multiply it by, let's say, k times m n l whatever w here, whatever. Okay.
Yeah.
Okay. First of all, this condition must be met that these are equal, then the definition that it's defined. Okay. Now the outcome here is going to be an n times w matrix. Okay. So here maybe in your question, I didn't hear you clearly. It's going to be 2 times 3, right?
Okay, my question is, let's say it's n times m
Yeah.
multiplied by, let's say, k times m.
Times m.
Yeah. So if
Yeah,
you multiply,
if m and k are equal, then it's defined and the result will be n times m.
okay.
Okay. But here in the middle, there must be equality, otherwise it's not defined at all. Okay.
Okay, so the outcome determines, the
Yeah, you put the dimensions here. You compare the inner values here inside. If the adjacent values, if they are equal, then it's defined. If it's defined, then this is the number of rows, this is the number of columns of the outcome.
Okay.
Clear?
Yeah, clear. Thank you.
Okay, now why it's done this way? Why it is defined this way? To demonstrate that, I think the best thing to do it is using a real life example. Okay, a real life example. So mathematics and algebra in particular always is taught using symbols, X, Y, W, whatever, A, B, C. These are abstract values, but of course the rules, the theorems are developed there. They can be just plugged in real life for concrete values. So let's do an example. Maybe this will explain how we come up to this way of multiplying matrices. So real life problem. Okay. So example, imagine you have, how you call it, a bistro or an M-Base shop that is selling 3 types of pies, okay? Of pies or sandwiches, whatever. And that the first type is beef and cost is per unit, let's say €3 each. Okay? The second type of pies, let's say it's a chicken, and it costs €4. And the third type, let's say it's vegetarian, and it costs €2 each. Okay? So assume these are the possible, let's say, items that are sold by this small shop, and we have registered for, let's say, 4 days the sales from each item, the number of items sold, let's say as follows. So here we have so let's assume 4 days, and here the items. So 1, 2, 3, 4 days. So let's assume here Monday, Tuesday, Wednesday, and Thursday. And here we have beef, chicken, and vegetable. Okay, so let's assume here we have this table, and these are the numbers recorded: 13, 9, 15, sorry. We said 4 days, right? 7 and 15. And here let's assume we have 8, 7, 4, 6. Then here 4, 0, 3, and here we forgot the 6. Okay. Now, if you want to find out, let's say, the total sales of this over the 3 days from each item, this is exactly the product of, if you put this here in one column or one row matrix, multiply it with here 1, 2, 3 times 4. Then you end up of having, for instance, if you want to find out what was the total sales for Monday, okay? Then what will you do? You go here, you have the sales for Monday, then you multiply logically the number of beef pies sold by the unit price of each. Then you do the same for chicken, you do the same for vegetables, and you add them up. So this will result on the total sales for this day. And the same you do it for Monday, for Tuesday, and for Wednesday. Okay? As you see, this is exactly what we did when we multiply the two matrices up there. I hope it's clear and it makes sense before I just write it. So the concept, is it clear? Total sales for each day, you just take the number of items sold there, multiply it with the unit price of each, add them up, and this is exactly what we did when we multiplied the two vectors as dot products. So if you like to do it as in a matrix form, then we will do here just, let's assume this is the matrix containing the unit price, and here €2, and we put all the items here or the units in one matrix. So let's say, sorry, 13, 9, 7, 15, 8, 7, 4, 6, and the last one here is 6, 4, 0, 3. Now before we perform the multiplication here or the product, let's check the dimensions of these two matrices. What is the dimension of the first matrix? Rows, columns?
The first one is 1 by 3.
1 by 3, exactly. And the second one here is
3 by 4.
3 by 4, exactly. So here is important. Maybe this answers the question of the girl who asked about the dimension. So here, first of all, it's defined because these are equal, okay? So this operation is defined, okay? Now the outcome here is going to be 1 times 4 matrix, okay? So the result here is 1 times 4 matrix. So the matrix here is 1. Has a dimension. That means it's going to have one column, one row, sorry, and 4 columns. Okay, 1 row and 4 columns. How to find this? Logically, the first item here will be multiplying this row with this column as a dot product, and this is exactly what I told you in the first step. So imagine if you want to find out the total sales for Monday, you multiply 3 with 13 beef, each €3, 8 chicken, each 4, add it to 8 veggie times 2, and this will give me the value for Monday or the sum for Monday. So here I have 83, can check it, and 63 and 37, and the last item is 75 euro. Okay, so here all in all 1, 2, 3, 4. So I have here this dimension of this one row, 1, 2, 3, 4 columns. Anyone has problem of finding out these values, or it's clear. So for instance, this 38 is the outcome of multiplying 3 times 13 plus 3 times 13, 4 times 8 plus 2 sorry, this is 6, right? This is 6. 2 times 6. Okay. So this is 39 and 32, right? And 12. So here you got 71 plus 12, 83. Okay. And the same you do it for the other items. So I hope with this example, with this simple example, you can find out, or it's clear why we did it this way. So because of the simple fact that it is it's the logic that we just explained in this particular exercise. There is another more extensive exercise, if you like, in page, I think, 4 in the script, titled matrices, that I took from our colleague, Professor Bob, and it can also explain maybe a little bit more extensive, and it is also okay. Good. Any questions? So we will do another example later regarding multiplication of matrices, but let me bring in here some notes regarding the product of matrices. Some remarks. Okay, first of all, multiplying two matrices A and reversing the order of the matrices is not always equal. In fact, sometimes one of them is defined, the other is not. Not only they are not equal. So this is in general the commutative rule here does not apply. Okay, so that's why if you are multiplying with the, let's say, inverse, later when we learn how to solve equations with matrices, you have to be careful. You multiply from the right or from the left because it makes big difference. And I see some students make mistakes there. So please here, multiplication from the side you are eliminating the matrix. Okay, the second thing here is that for square matrices, remember, are matrices that have the same number of rows and columns. Square matrices of the same dimension multiplication is always defined because they have same number of rows and columns. And not only that, you have also the result, it's going to have the same, logically the same dimension. Okay, so here for instance, if you have a 2 by 2 matrix, A, B, C, D, let's say a 2 by 2, you multiply it with another 2 by 2, E, F, G, H, for instance, then you will expect, so this is a 2 by 2, This is a 2 by 2. So product is defined if you have multiplying two square matrices with the same dimension, and the result here is going to be a 2 by 2. So here you will be having a 2 by 2 matrix as a result. You got it? So multiplication of square matrices from the same dimension is always defined. Okay, and another thing is that multiplying a matrix with the identity is equal the matrix itself. Here, identity, where A here is square matrix, which has the dimension n times n, and notice that here the identity, there is not only one identity here when we talk about matrices. It's not like numbers, you say one is the multiplicative identity. Here we are talking about identity corresponding to the dimension of the matrix. Okay, so identity here in general, we defined it in the previous lecture. So it's actually the square matrix where you have here ones along the main diagonal and you have 0 everywhere. Okay, now what I'm going to do, I'm going to distinguish these identities simply by just writing here a subscript that will indicate the number of rows and columns in this. For instance, we will be using I2, for instance, for this identity. Don't know whether you can see this. Yes, okay. So 1001. Okay. I3 is equal to 10001001. Okay, and so on. And now here, if we apply the product here, you will be having just multiplying everything out. So you multiply the first element with 1 and all others are 0. So that's why you will be having the first element here the same like A in the product matrix and so on. So that's why it will generate the original matrix. Is this clear? So multiplying by the identity will result in the same matrix.
Yes, sir.
Okay. Now another thing about squared matrix, sorry, multiplying by identity, it will be also the same if you multiply it from the left or from the right. So here I just write it here. I multiplied by A is equal A multiplied by I, which is not always the case as we just noted in the first note here. Okay, now let's talk about what is the inverse of a matrix. This is the tough topic there. What is the inverse of a matrix? Before I start, inverse of a matrix, inverse of matrices. First of all, inverse makes sense is defined only for square matrices. With, this is an important note, it's not only defined, it's not only enough that a matrix is square matrix to have the inverse defined. With determinant for a square matrix, let's say matrices with determinant not zero equal to 0. Okay? So for being able to evaluate the inverse of a matrix, we need, first of all, to check two things. Is the matrix square matrix? Then it's possible, but this is not enough. Further, we need to check that this identity, this determinant or the determinant of this matrix is not equal to 0. So two conditions here must be checked before you start talking about or evaluating an inverse of a matrix. Now, evaluating the inverse of a matrix is something, let's say, that gets a little bit more tedious, more complicated if we talk about higher dimensional matrices. However, for a 2 by 2 matrix, I will give you a shortcut. Of course, this is not because it has a proof. It has proof. You can Google it if you like. So let's start with an inverse of 2 by 2 matrix. Okay, so let's assume A is the matrix that has the 4 elements. It's a 2 by 2 matrix, A, B, C, D. And let's assume that the determinant of A is non-zero. Okay? Then A inverse is equal to 1 over determinant of A multiplied by D minus B minus C and A. Okay, to evaluate the inverse of a 2 by 2 matrix, we evaluate the determinant, multiply with the reciprocal of that, and you know that we defined it last time. This is a constant here. That means it will be expanded here to all elements of my determinant. Sorry, of my matrix. Now, what we did here, we just exchanged the positions of these two elements along this diagonal, and we kept the positions of the other diagonal, but we changed the signs. So here you have negative and here negative. So C and B remains there, but we change the sign. A and D, we switch the order while keeping the sign. And in this way, we get the determinant of a matrix. Now I will leave it to you. Maybe here two things. First of all, determinant of A, we learned it before. Determinant of two-dimensional matrix is AD minus CB. I think this is clear for everyone. This is how we defined the two-dimensional determinant. Another thing here is that if we multiply the inverse matrix with the matrix, the original matrix, or we just do it the other way around, we end up of having the identity. In this case, the two-dimensional identity. So 1, 0, 0, 1. So I want you to check that. So to do this as an exercise, check whether this matrix multiplied with this matrix is going to give me the identity. You can just do it from the right or from the left. It doesn't make any As you see here, it doesn't make any difference because in this particular case, it is commutative. However, it's not always that way. Okay. So determinant of a 2 by 2 matrix is straightforward. Let's take an example. Questions so far? Okay, so assume you are asked to evaluate the inverse. Of course, it's difficult now to write it on the chat, but example. Evaluate A inverse where A is equal to this 2 by 2 symbol matrix 4, 7, 2, 6. Okay, now to solve this, the first thing you do, okay, it's a 2 by 2 matrix. We check the determinant of A. Who's going to tell me what's the determinant of A? What is the determinant of A?
It should be 1 over
No, the determinant. Not 1 over, just the determinant.
4 times 6
Exactly.
minus 7 times 2.
2 times 7 or 7 times 2, and 24 minus 14 is 10, right?
Yeah.
Okay, so A inverse is equal to 1 over the determinant, 1 over 10, multiplied by, now we need to apply the rule that we learned before. So switch the order of these. So here you have 6, here you have 4. Okay? Change the sign here, -7, -2. Now here, if you like, this you can just write it as a fraction. If you like, it's 6 over 10, -7 over 10, -2 over 10, 4 over 10. Okay, you remember the rule here, you need to expand all. So this constant here, you just expand it here to all different values. So this is, we learned last time how to multiply a matrix or a constant by a matrix. Of course, here you can just write it as decimal if you like. I don't know. Sometimes students they like decimal, sometimes they just prefer the fraction. So minus 0.2 and 0.4. Okay, so this is the inverse. Now let's check it. Okay, let's do this exercise and check it from one side. So we check if, for instance, A multiplied by A inverse, is it equal to the identity? In this case, the two order identity. Okay, let's put this in order. So here 4, 7, 2, 6. I multiply this. Let me take the decimal here. It's easier to work with. So 0.6, -0.7, -0.2, and here 0.4. Okay, first of all, we are expecting here 2 by 2. I said, well, if you have square matrices, you multiply them with the same dimension, of course, multiply them with each other, you end up of having the same dimension. So here we are expecting a 2 by 2 matrix. I hope it's clear for everyone. Now, what are the elements of these 2 by 2 matrices or matrix? Let me just plug in the power here. Okay, so first term here, it will be 2. Sorry. Okay, so I again remind you how we do it. We multiply this row with this column, okay? So here we expect 4 elements, so let's make some room here maybe. Okay, so first one is 4 times 0.6 plus 7 times 0, negative 0.2, right? This one here, it will be, I need 4 room. So let me just make it here down maybe. Okay, so here again, 4 times 0.6 plus 7 times negative 0.2. Okay. Now the second element here, I multiply this with this one. So here 4 times negative 0.7 plus 7 times 0.4. Here I go to the second, so this one we are done. Now here I go to the second row, multiply it with that one and that one to get the second row here. So 2 times 0.6 plus 6 times negative 0.2. This one here, 2 times negative 0.7 plus 6 times 0.4. Okay, so let's evaluate them here one by one. So 4 times 6, 0.6 is 2.4, right? Plus minus 1.4. So the result here is 1. This one here is negative 2.8, right? Plus 2.8. So the result here is 0. Here I have 1.2 minus 1.2. The result is 0. And here I have 1.4 minus plus 2.4. And this is 1. Okay, so the final result here is indeed the identity matrix. Now, this way you check that a given matrix is the that a given matrix is the inverse of the other. It's just like, how do I know that 5 and 1/5 are inverse to each other? I multiply them out and I get the identity, okay? Okay, so now evaluating inverse in this environment, I'm talking about the matrices environment, is even more important because we don't have division, okay? So don't have division at all. So you multiply with the inverse to get rid of the number. So for instance, I will just show you why is this more important here. Imagine you are solving a matrix equation, okay? Now, let's take a linear system that is given as in a matrix form, okay? And we want to solve it, okay? Solve here. And the A X and B are matrices. It's not number. Okay. So usually you have A is the coefficients matrix, and X is the variables matrix, and B is the right-hand side. Okay, now if you want to solve it, so if you want to follow the same scheme like we did for numbers, that means here you want to solve for X equals, so this is how we proceed if we want to find the solution, right? But the thing is here, we don't have division, right? In numbers, we said, well, okay, I will divide this by 1 over A, and then this will give me 1, and I saw a divide both sides, of course. Here, I can't do that, okay? But to get rid of this A to the left here, I multiply with A inverse, and then I multiply, of course, the right-hand side with A inverse. And this will give me here I, of course, but the identity multiplied by any number, any matrix, sorry, is the same. So this is going to solve the linear system for me if I know the determinant, the inverse of any matrix of the coefficients matrix. So that's why this is a way to solve the linear system. I hope everyone got this. If you like everyone got the, let's say, it's not a trick, it's the way to get over the fact that we don't have division here. No problem, then we multiply by the inverse to get rid of numbers we don't want. So usually we will be having lots of equations that we will be solving involving the different types of matrices. And to solve these, we need to, of course, carry out operations just like we do with numbers. But here we have only 3 operations, and we have the operations defined only for specific types. I think there's one of these that we solved today, but we will get more let's say extensive exercises as we proceed, maybe next week or the week after. Okay, I think at this stage we can stop and take a small break. Then after the break, we will get a real life example how to solve a system using A inverse. Okay. So as you see here, this is the solution of the linear system. All I need to do, if I know A inverse, multiply with the right-hand side, and then get the solution matrix. Bear in mind that this capital X here, it means the variables X, Y, Z, etc. Okay, so after the break, we will start with a real-life example that will give us the, let's say, feeling of how to solve linear systems using the inverse of the coefficients matrix method. As I mentioned, there's one more method left, which is using determinant. It's called Kramer's rule that we will do next week. Okay, so for the next session, we will focus on doing this. And of course, here our real life problem will be straightforward using the 2x2. Then I will show you how we use the reduction algorithms by Gauss to evaluate, let's say, 3x3 inverse. So as I told you, when it gets to large, let's say, dimensions like 4, 5, etc., the process of getting the inverse of the matrix is going to be more tedious and very complicated. Okay, so let's make a break and get back at 11:30 to continue with the inverse method. Any questions? Let me check the... Okay, repeat this. What do you need me to repeat? Now you got it. Okay. All right. Okay. So let's take the break and then in 15 minutes we will continue. Thank you.
Thank you.
Okay, so let's continue. You can hear me now?
Yeah, we can hear you.
Yes. Okay, so as I mentioned before the break, we are going to have a real life example how to solve a linear system using this equation here. That means here, if you have a linear system, of course, in this form, the matrix form, you evaluate the inverse of the coefficients matrix, you multiply it by the right-hand side matrix, then you achieve a solution for this. Okay, so let's take an example. So as I mentioned, it's a real life example. It means in this case, you know, also the challenging thing in real life examples is that you need to construct the equations yourself and then start solving. So let me just make it describe the example here. So a group of people on a trip. So they took a bus with the price €3 per child and sorry, and €3.2 per adult. Okay, the total of this trip was for a total of 118.4. On the way back, the same group, same number, they took train. Okay. And the cost per child there was 3.5 euros for a child and 3.6. Of course, here when we're talking about currency, it's 60, 20, 30, but I just work with numbers with one decimal here because the zero you can, of course, just cancel. So per adult for a total of slightly more here, 135.2. Okay, clear? So a group of people, they went on a trip going, they took a bus, €3 per child, 3.2 euros per adult, and the total was 118.4 euros. On the way back, they took a train at 3.5 euros per child and 3.6 per adults, and the total was 135.2 euros. Now the question is, how many children were this in and how many adults were in this group. Of course, as I mentioned, so as I mentioned, assuming, of course, that the number of in the group the same number, okay, that the numbers of children and adults who took the bus is the same that they took the train on the way back. Okay, so imagine you have such question. These questions are really I like to bring them because you are future engineers, and then you will be dealing with real life problems. And here we are not teaching you, let's say, abstract mathematics all the time. So just make some real life examples to see how the challenge there is to get the equations out of this description of the problem here. Okay, so if you were to solve this, what is the first thing you are going to do? Of course, after reading this carefully, anyone can say or write what is the next step, the first step. What would you do? No idea? There we have very few online. I hope this will not be always this number. So tell me, what would you do? Let me get this page here, maybe. If you want to try this, solve this problem, what would you do? So you are asked to, you don't know how many children, how many adults. So translate this problem into, let's say, symbols, right? So the first thing, you assume that let X be the number of children in the group, right? You can take any other variable, and Y be number of, let's say, adults. Then you construct the equations. Okay, the first equation says that I don't know how many children, but 3 euros per child plus 3.2 per adult, and the sum was 118.4. Okay, so first you introduce variables, and then you translate the text there into equations. The second equation, it says on the way back, this same X multiplied with 3.5 euros each plus 3.6 Y here, and the total was 135.2. Okay. Now we will solve this using the inverse method. Okay. Are you saying something? I can't hear anything. I don't know why she has LO as a name. So just keep your name, because if I just take some notes, something, I know whose account is that. Okay. Now, the first step here is to write. So first step, write the system, the linear system, in the so-called matrix form. And I hope it's very straightforward. I hope it's clear for everyone. So what you do here is you take the coefficients, these coefficients, and you just put them in a matrix. Okay, so in this case, it means A capital X equals to B. So this is the general form. And my particular example here is 3, 3.2, 3.5, and 3.6. Okay. Then multiplied with the capital X here is the variables in one column or one matrix. And B is just the right-hand side, which is these two numbers here in one column. Okay, so this is how you transfer a linear system to the so-called matrix form. I think this is straightforward, and no one should be having difficulties with this step, I hope. Okay, so this is my A, if you like. This is my A. This is my X, and this is B. Okay, so this is A, this is X, this is B. Now, A inverse, according to the rule we learned before, is equal to the first thing. What is the determinant here? So it's 1 over the determinant. 3 times 3.6 minus 3.5 times 3.2. So this is the determinant. 3 times 3.6 times 3.5 times 3.2. And then here we need to apply the rule. So here I flip this diagonal, negate this diagonal, negate this one, and this one is just 3. Okay. Now I don't know what I get here, so I evaluated this somehow here somewhere.
-5/2.
Yeah, it is. I just evaluated everything here, but important here, maybe I will write it here, check determinant of A is not equal to 0. So obviously this is not equal to 0. I don't know what you get here, but I evaluated all this as -9, 8.5, sorry, 8, 8.575 and -7.5. Okay, so this is the inverse. You can check it if now I know the inverse, so the solution here, the solution is xy or x is going to be, according to the rule, A inverse multiplied by B, but here I have A inverse, which is -9, 8, 8.75 and -7.5. Okay, and I need to multiply this with the right-hand side, which is 18.4, 135.2. All right? So this is how we solve the system. So notice here that when you solve it, you will be getting a 2 by 2. First of all, verify that this is possible. So this is a 2 by 2, and this is a 2 by 1. So what I'm going to get here is a 2 by 1 matrix. That means it has 2 rows and 1 column, which will be just the first row will represent X, the second row will represent Y. Okay, so carrying out this multiplication, I think it's straightforward. So you just multiply this one with that one. So you get negative 9 times 1, 18.4 plus 8 times 1, 35.2 in the first row. The second row, you multiply this one with this one, you got 8.75 multiplied by 11.4, and then you got negative 7.5 multiplied by 135.2. Okay, so let's see. Okay, so this is equal, so x equals xy equals 2. I will multiply it out, so the result of the multiplication, so here I got, what was it? Here I had to the left. Let me just check it again. Okay, so it's negative 9, 8. Okay, negative 9 multiplied by 118.4 plus, of course it's minus here, but no, it's plus 8 times 135.2, and in the second row here you get 8.75 multiplied by 118.4 plus minus 7.5 multiplied by 135.4. Okay, so anyone can evaluate these values? This here, first line. 16 and 22. Great, thank you. 16 and 22. And notice that this is capital X, which is the variables X, Y. And you remember it means here to interpret this that X equals. So it follows that we have, is it 16, 22 or 22, 16? 16, 22. So it follows that we have 16 children. Remember, this is the original question here, right? How many children, how many adults? So you need to answer this. Now you can go and verify and check. You can just go and then multiply 16 with 3, 22 with 3.5 and see whether you will be getting the sum 118.4. You go multiply 16 with 3.5, add it to multiplying 22 with 3.6 and see whether you will be getting 135.2 here, of course. Okay, so this is how we solve problems using the inverse of a matrix. Any question regarding this before we move to a little bit more Okay, so I see your group not asking questions, meaning you're very good and you know everything, or you're just not following. By the way, it's not snowing here in Farkirchen. If you are not in Farkirchen, snowing heavily. Okay, now let's see how or I will give you an example where the inverse does not exist. The inverse might not exist. As in the following example. So here you just have 6, 4, 6, sorry, 3, 3, 4, 6, 8, obviously. Okay. Now the first thing you do here is the determinant of A is equal to 24 minus 24, so it's 0. So notice that if you want to apply this rule, then we will be having, okay, you will be switching these two positions. So you get here, according to this, A inverse is going to be 1 over the determinant of A. And then here you just switch 8, negative 4, negative 6, and 4. Sorry, 3. Okay? But here you will be having 1 over 0. Which is a problem, okay? So that means here, if the determinant of any squared matrix is equal to 0, that means A inverse does not exist. Okay, so don't try to evaluate or to find the inverse of a matrix that is equal to 0. Okay. Now, before I move to a larger matrix, do you have any questions regarding this process? Is it clear how this process works? Write the linear in order to solve the linear system using the inverse matrix. You just write the system as AX equals B in what we call matrix form. Try to evaluate the inverse matrix and then just multiply it from the left with the right hand side, if it exists, of course. And this is the solution of the linear system. Now, we saw, luckily for the 2 by 2 matrices, evaluating the inverse is not that complicated. However, for 3 by 3 matrix, there is a rule for this, but it's not as let's say, simple and straightforward as the 2 by 2 matrix. Usually, to evaluate the inverse of 3 by 3 matrix, we will use the Gauss elimination method, okay? Or the Gauss-Jordan method. So, now remember the Gauss method, and Gauss method means using the elementary row operations. Remember these three operations on rows that we used in getting a system in echelon or reduced echelon form. You can multiply or divide by any non-zero number. You can add 2 rows or subtract 2 rows, and you can flip the order of any 2 rows. Is what we call the elementary row operations. Now here, to evaluate the inverse of a matrix, what we do is we will be forming a new matrix, which is what we call the